All right, guys, today is August 1st. What we're going to do is we're going to continue in our notes from topic 9.1 where we left off yesterday. So if you'll get those out in front of you, you can pause the video while you do that. And what I also want to go over with you is your pre-lab homework for tonight, because tomorrow you will be doing a lab, which seems crazy to do a lab while I'm not there, but the sub has been, he knows what to do. And it's actually a super easy lab. So if you want to pause the video now and get the lab from him, and then you can come back and we'll go over it. All right, so just as a reminder, what's due while I'm away. Today you're gonna watch this, and then for homework you have your single replacement lab. Tomorrow you'll do the lab in class. It's super easy. Basically, you're just putting pieces of metal in liquids and watching what happens. So it'll take all class period, but it's not complicated at all. And then you are going to write a lab report on this lab, and it's due on the 11th. And then tomorrow, or not tomorrow, but Tuesday when you come back, because we don't have school on Monday, you'll have all day in class to work on the lab report. And then for the rest of the week, you'll just watch the lessons on Schoology. So for your lab, what I want you to do for homework tonight is in your lab notebook, give the lab a title, and then you're going to write the full balanced chemical equations for your assigned chemical reactions, determine the oxidizing and reducing agents, and then predict whether or not the reaction will occur. So if you guys will look at your lab paper with me, what I'm going to do is I'm going to tell you which chemical reactions you're responsible for. So this is the format that I'm looking for you to write your chemical reaction equations, and then once again to identify what's being oxidized, what's being reduced, and therefore the oxidizing and reducing agents. So in this equation, M represents the metal and X represents the least reactive metal, where X, you see the state of matter is an aqueous solution. So that is the solution that you'll be placing your solid metals in. So when you write your equation, when I tell you your chemicals, whatever solid you're placing in there, you're going to put that, replace that for M, and whatever liquid you're using, your solution, you're going to replace X with that. So if you flip the page, these are the chemical reactions you're going to be observing. So the person or the group that's going to do the magnesium metal, you're going to take this magnesium metal and you're going to put it in 4 different test tubes. The 4 different test tubes have magnesium nitrate in one of them, zinc nitrate in another, iron nitrate, and then copper nitrate. So this group is literally, you're just dropping a piece of magnesium in 4 test tubes and watching what happens. Like I said, it's not complicated at all. So Anthony, your table is doing, actually, you're going to do 2 metals. You're going to do magnesium and copper. So you guys can kind of split into 2, I guess, and but your table is responsible for magnesium and copper. You guys can decide who's going to do what. Arabella, your table is going to do zinc, and then Mason's table, you guys are going to do iron. When you put them in, the reaction may not be spontaneous. It may take a while. So kind of wait until almost it's time to go to look at the changes inside your test tube. And you're going to look at everybody's test tube. So even though you only put magnesium metal in the test tube, you still need to visit the other students' test tubes so that you can fill out your whole data chart here. So to actually perform the lab maybe takes 5 minutes, but then you'll have to wait until kind of the end of class. So during that time, if you wanted to, you could work on your pre-lab questions or grab a laptop and start writing up your lab report. But then at the very end, probably I would say 15 minutes before class is over, make sure you guys go and you look at the test tube so that you can write in your results. Then when you're finished, you're going to write your conclusion. So you're going to answer this in your conclusion and the for consideration. Now, the first one, when it says compare your conclusions to the electrode data and comment, they're talking about in your data booklet. So in your data booklet on section 24, you can see, like here's magnesium. So this is the magnesium metal. That's the electrode potential for the magnesium metal. Okay. So you're just going to comment on the electrode potentials of your metals. Make sense? All right, so that is basically what you're going to be doing for your lab, and then that's what you're doing tomorrow. So today what we're going to do is we're going to pick up where we left off yesterday. So we talked about oxidation stage yesterday, and today what we're going to talk about is the IUPAC system. So you guys will find this slide in your notes. Basically, you guys you're already familiar with the IUPAC system, but what we do in this system is we take the oxidation numbers that we determine, like I showed you yesterday, and whatever the oxidation number is, you replace that with a Roman numeral. So, for instance, oh, I'm sorry. Here, let me show you an example. Okay. So you can just write this on this slide that you have right here, this kind of open space. All right. All right, so we're going to figure out the names of these compounds and then use the IUPAC system to name them. So if you want to get out your periodic table, you can pause the video to do that. This first element we have is V, so we find V on the periodic table, and it is vanadium. And then oxide. Now we got to figure out the oxidation number of vanadium, and once we do, we're going to put that in parentheses there. Right, so the way we're going to figure out those Roman numerals is what we did yesterday. So the overall charge of this compound is 0. Oxygen has an oxidation state of -2. So there's 5 oxygens, each with a -2 charge. That's a total of -10. There's 2 vanadiums with some charge. So just take your -10, divide it by 2, and that gives us a charge of 5. So then we write our Roman numeral for 5, which is V. And if you don't know your Roman numerals, you need to at least know them for up to 7. So that's how you do that one. Now for this one, we have Ni, which is nickel, and OH is a polyatomic ion. You should know this one, but that's hydroxide. So now we need to figure out the oxidation number of nickel so that we can put our Roman numeral in there. So hydroxide has a charge of -1. there are oxidation number of -1. There's 2 of them, so that's a total of -2. There's only 1 nickel, so to cancel with -2, nickel needs to be +2. So why don't you try C, titanium chloride there, and you can pause the video and come back and check. All right, so to figure it out, we have a neutral compound. Chlorine has an oxidation state of -1. There's 4 of them and only 1 titanium. So that's a -4 charge for our total for chlorine. Only 1 titanium, so to cancel with that -4 would have to be 4. Awesome. All right, so I'm gonna put some more practice on the board and I want you guys to try these on your own. All right, so I want you to try these on your own. So pause the video here and then come back and check on it in just a second. All right, so check your work. How did you do? D is cobalt-3 fluoride, vanadium-3 oxide, copper-2 hydroxide, manganese-2 oxide. Oh, manganese-4, sorry, manganese-4. So how did I get 4? Well, oxygen is -2, or oxidation state is -2. There's 2 of them for a total of -4. Manganese must be +4 in order for it to give us a 0 overall charge. H is copper-1 hydroxide. So oxygen, oxidation state is -2. Copper is some charge, and there's 2 of them. So -2 divided by 2 gives us 1. So that's how we get copper-1 oxide. All right, so next in our notes, we're going to talk about how to interpret oxidation states. So anytime, and this can get kind of confusing because there seems to be like some conflicting things happening. So basically what we're looking at here is whenever there's an increase in the oxidation number, or when you see an oxidation state on the reactant side of the equation increase on the other side, like for sodium here, how it goes from 0 to +1, the oxidation state is becoming more positive. When that happens, it represents oxidation. When you look at chlorine here, chlorine's oxidation number on the reactant side goes from 0. And then on the other side, the product side, it becomes more negative. That represents reduction. So the best way to remember this is just the word reduction itself. If something's getting reduced, it's going to get smaller. So if you see an oxidation state become more negative or become smaller, then it's undergoing reduction. If you can remember that, remember if it's undergoing reduction, the other thing must be undergoing oxidation because the two come in together. So if chlorine's undergoing reduction, that means that sodium has to be undergoing oxidation. Now, the next slide is where it gets a little complicated, but not really, so don't freak out. All right, so reduction, oxidation reduction reactions occur simultaneously, like I said. The reactant that accepts the electrons is called the oxidizing agent because it brings about the oxidation of the other reactant. So like I said, that sounds really confusing, but basically this yellow highlighted statement here is all that you need to remember from this slide. The substance that's getting reduced or becoming more negative on the product side is called the oxidizing agent. So if it's undergoing reduction, that thing is the oxidizing agent. The substance that's being oxidized or becomes more positive is the reducing agent. So the thing that's becoming more positive on the product side is undergoing oxidation, which means that that thing is the reducing agent. So let's take a look at a couple of examples. Hold on, I gotta find my place in my notes here. Okay, here we go. All right, so this is actually something that you need to do for your pre-lab homework. And also something that you're going to experience in your lab, because in your lab you need to be able to identify the oxidizing and reducing agents. So this is good practice for that. All right, so here we have zinc. Its overall charge, an element by itself. Oxidation state is 0. Here is copper. It's an aqueous solution, so there's probably an anion attached to this that's not important, like nitrate or sulfate, because that's going to stay the same in the chemical reaction equation. So we're really just focusing on the metal, the cation involved. So copper, you can see the oxidation state right there, 2+. Zinc on the other side, 2+. Copper now is a metal by itself, an element, so 0. So if you look at zinc, zinc's charge oxidation number is going from 0 to +2. So it's becoming more positive. So is that oxidation or reduction that becomes more positive? Oxidation. So the oxidation half equation is where you just focus on these two things. So we have zinc on the left-hand side, producing zinc 2+ on the other side. Okay. Now, copper, if zinc is undergoing oxidation, copper should be undergoing reduction, which if you look at the oxidation states, it's going from 2+ to 0. So it's being reduced. So that is your more negative, that is your reduction half equation. So we have copper on the left-hand side, so that's going to stay on the left-hand side. And copper solid on the right-hand side. Now we're actually not quite done, because when you balance the chemical reaction equation, you need to balance not only the subscripts and the number of zincs on each side, but also the charges. So over here, the charge is 0. Over here, the charge is 2+. So to balance it, I need to add negative electrons to the side that's more positive. So if I add 2 electrons over here, I now have 2 positives from zinc, 2 negatives from the electrons to give me a total charge of 0, like my zinc over here. Now for the bottom equation, I have 0 on this side, 2+ on this side. Once again, you want to add electrons to the more positive side, so I'm going to add 2 electrons to this side. So now I have 2 negative electrons Two positives give me a total charge of 0. And then your electrons should cancel out. Electrons you'll see on the right-hand side of an oxidation reaction, left-hand side on the reduction equation. So now let me ask you a follow-up question. What is the oxidizing agent? And what is the reducing agent? So remember from the previous slide, if zinc is undergoing oxidation, that means it's going to be the reducing agent. So zinc is your reducing agent. And here, if copper is undergoing reduction, then that means that this is your oxidizing agent. Your reducing and oxidizing agents are always going to be reactants, okay? So because once again, zinc is the one undergoing oxidation, it's going to be the reducing agent. Because copper is the one undergoing reduction, it's going to be the oxidizing agent. We'll get more practice with this in just a moment. All right, let's look back at your notes. All right, so the strength of these oxidizing and reducing agents, you can actually see them in the activity series, and that's actually what how the activity series is made, is based off of the strength of the oxidizing and reducing agents. So in your data booklet, if you want to flip to page 25, you can pause the video while you get your data booklet to do that. You'll see the activity series on page 25. So this is an activity series of metals. And remember, metals are the ones that lose electrons and form positive ions. So they're becoming positive. So because they're becoming positive, they're the ones that are undergoing oxidation and therefore are reducing agents. So in our activity series here, you've learned about the activity series in honors chemistry, but the element at the top of your activity series, the one on your screen is potassium, the one in your data booklet is lithium, only because they're like, different sources. But anyway, the one at the top of the activity series is the most reactive metal. That's where you're going to find the strongest reducing agents because they're the ones that get easily oxidized. As you go down the activity series, you see gold at the bottom there. It's the least reactive metal, which is one reason why we use it so much in jewelry, because you can put it on your skin. It's not going to react with any soap or chemicals like shampoo or basically anything. It's fairly unreactive and not get easily oxidized, which is one reason why if you have gold jewelry, it's not going to ever turn green on you like copper, which is higher in the activity series and is more easily oxidized. So I'm going to ask you a couple of questions about the activity series just to make sure that you understand how it works. So on the next slide, we'll go over some examples. Right, so we're going to use the activity series to figure out whether or not this reaction will occur. So looking at your data booklet, what we need to do is we need to find the element that's by itself, which is here, silver. It's not in a bond. We need to figure out this placement of silver on our activity series in relation to the metal that's in the compound. So if we look at our activity series, we can see that silver is down here on the activity series and zinc is way up here. So zinc is the better reducing agent. So it can replace silver, but zinc is already bonded with somebody. So really it's seeing if the element by itself, silver, if it's higher on the activity series, it can replace the one that's in the solution. But because silver is lower on the activity series, it is not strong enough to reduce zinc. So this reaction will not occur. So in your lab tomorrow, you're going to do exactly this. Once you know your chemical reaction, so once again, this is the metal you would place in this liquid test tube. If the metal that's by itself that you're placing in the test tube is higher on the activity series, then the reaction will occur. If the element is lower, like silver in this case, it will not be able to replace the one in the solution. So let's look at another example. Okay. So once again, focus on the metal that's by itself and find it in the activity series. So in this case, it's magnesium. So here's magnesium here. And we need to find iron. So here's magnesium. Iron is lower. So in this case, the metal that's by itself in this reaction, magnesium, is higher than the one that's in the solution. So that means that magnesium can replace iron. So this reaction will occur. And so you'll see, you know, bubbles or a precipitate, or you'll feel the test tube and it's going to be hot. This reaction will occur and you will see those chemical changes. So tomorrow, you're basically testing to see if the activity series holds true with your series of reactions. Now, we can also do this with nonmetals. So when we take a look at nonmetals, you'll see in your data booklet that there's not an activity series for nonmetals. And that's because if you look at your periodic table on section 8 in your, or 6 in your data booklet, you'll see that group 17 is your activity series. And it works the same way as the metals. The ones that are higher in the activity series or in group 17 can replace the ones below, except metal or halogens are the opposites of metals. So whereas metals are reducing agents, nonmetals are oxidizing agents. So fluorine is the strongest oxidizing agent and can reduce the ones below. So let's take a look, keeping this in mind, let's take a look at some examples with nonmetals. Okay, so it works the same way as above. So you find the halogen that's by itself, which is chlorine here. And you see where it is in group 17 in relation to the halogen it's trying to replace, which is iodine. So if you look in your periodic table chlorine is higher than iodine. So because the element by itself is higher than the element it's trying to replace in the compound, this reaction will occur. Once again, because chlorine is the strongest oxidizing agent. Okay, so the last thing I want to talk to you about today is writing redox equations using half equations, which is what we did prior when we were identifying the oxidizing and reducing agents. Now, this slide seems very scary and overwhelming, but it's really not that bad once you start going through the process. But the first thing you have to do is assign oxidation states, which you already know how to do. Then you write the half equations for oxidation and reduction, which you already know how to do. Then you go through and you balance any atoms that need to be balanced other than hydrogen and oxygen. So if you have copper in there, you need to balance your coppers and so on. Then you balance the half equations for any oxygens in any of the half equations by adding water as needed. So if you have 2 oxygens you need to balance, you'll have to add 2 waters because every water only has 1 oxygen in it. Then you balance each half equation for hydrogen by adding the hydrogen ions as needed. So if you need 2 hydrogens, then you'll add 2 hydrogen ions because there's only 1 hydrogen in a hydrogen ion. Then you balance the half equations for their charge by adding electrons like we did before. Then you check that each half equation is balanced for atoms in charge, and you equalize the number of electrons in the 2 half equations by multiplying appropriately. So like if in one half equation you have 1 electron, in another one you have 2, you'll have to multiply the 1 electron equation by 2 so that they can cancel. So that's the overall gist. Like I said, it's scary until you see it in action. So this is going to take up a lot of space. It's probably going to take up the whole next slide that you have, just at least for the first one so that you can see all the steps in place. So let's take a look. So this isn't something you have to worry about for your lab tomorrow. Everything that we talked about before is something, you'll have to know when you do your lab. This is not what you're doing tomorrow. So you don't have to worry about if you don't understand this today in order to do the lab tomorrow. All right, so what we're going to do is we're going to start by writing a reaction equation. So we're reacting these 2 things together. So NO3 plus Cu, and we're going to produce NO and Cu2 plus. Okay. So now, if you look back at your first step in your slide, we need to determine oxidation states. So copper, we can see, goes from 0 to 2 plus. So is copper being oxidized or reduced? It's going from 0 to more positive. So that would be oxidation. So this is going to be your oxidation half equation, is taking copper Remember, if it's a reactant, it stays on the reactant side. If it's a product, it stays on the product side. So if copper is undergoing oxidation, that means that NO3 must be undergoing reduction. So pull that out like so. All right, so the next thing we have to do is balance all of the elements other than oxygen. So I have one copper on this side, one copper on this side, one nitrogen on this side, one nitrogen on this side. So everything's balanced. Now I balance the oxygens by adding water to one side or the other. Now this equation doesn't have oxygen, so I don't even try to touch it with any kind of water because that would just be an issue. Down here, though, I have 3 oxygens on this side and only 1 oxygen on this side. So I need to add 3 waters, or I'm sorry, 2 waters on this side. Because now I have 1 oxygen here, 2 oxygens from water, total of 3 to cancel with my 3 over here. Now I can balance my hydrogens by adding H pluses. Once again, I don't have any hydrogens in this equation, but I do here now that I've added water. So I have a total of 4 hydrogens on this side. So I need to add on the other side 4 hydrogen ions. So now I have 4 hydrogens on this side, 4 on this side. Once I do that, now I can balance my charges. So here my charges are not balanced. I have 0 on this side and positive 2 on this side. Remember, you can only balance charges by adding electrons, which are negative. So you want to add them to the more positive side. So if I have 2 positives here and I want it to be 0, I need 2 negative electrons. So now this equation is balanced. Down here on the right-hand side, I have a 0 charge. On this side, I have 4 positives and 1 negative, which brings me to 3 positive. So I got to add 3 negative electrons on the left side so that 4 negatives plus 4 positives gives me a total of 0, like over here. Now I'm almost done. The last thing I need to do is I need to cancel out my electrons. So in the oxidation, I have 2 electrons that are being transferred, but here I have 3. So those do not cancel. So I got to find the least common denominator, or least common multiple, whatever the term is, which would be 6. So I'm going to multiply this one by 3 and this one by 2. And I'm just going to rewrite it because this is getting a little crazy. And I'm going to distribute that to everything. So that would be 3 coppers, 3 Cu2 plus, and 6 electrons. Down at the bottom, that's 6 electrons. 2 times 4 is 8 hydrogen ions, 2 NO3s, 2 NOs, 4 waters. Okay, so now we cancel anything. So those cancel and then we add it all together. So here are my reactants that need to stay on the reactant side. So 3 coppers, 8 hydrogens, 2 NO3s, and the products stay on the product side. So this is all that's taking place whenever you react these 2 reactants together. We don't really see it because it's happening in solution, but this is everything that's going on in your reaction. All right, let's do one more. here we are. So, if we look at iron, iron's going from 2+ to 3+. So what's happening with the charge? Is it, or the oxidation number, is it going up or is it coming down? It's going up. So that means iron is being oxidized or reduced. Oxidized. So that's your oxidation. Which means the other thing is undergoing reduction. All right, so now, once again, start with your oxygens by adding water. No oxygens here, 4 oxygens here. So I need to add how many water molecules to the right-hand side? 4. 4 water molecules. Now I balance my hydrogens. I have no hydrogens here, so I'm not going to add any hydrogens there. But I do have a total of 8 hydrogens now. So on this side, I need to add 8 hydrogen ions. Now I balance my electrons. So I have 2 +2 charge here, +3 charge here. So I need to add only 1 electron. So now this is 2 positive and this is a 2 positive. So down here, I have 2 positive on this side, 8 positive on this side. So I need to bring this down so that it's only 2 positives. So what do you add to 8 to bring it down to 2? 6 negative electrons. So then you go through and you make sure that your electrons will cancel. So I need to multiply this one by 6. So now my electrons will cancel. And your overall equation will be 6 Fe2+ plus 8 hydrogens plus MnO4 yields 6 Fe3+ plus Mn2+ plus 4 waters. See? It's really not that bad once you do a couple of practices. So I'm going to give you one more, or no, I'm not. That's it. We're not going to do any more of those. But I do have a worksheet to give you. So if you will ask the sub for it, you can work on that. And then tomorrow, probably while you're waiting for your reactions to take place in your lab, we can go over the worksheets and your chemistry of the week. We'll do that tomorrow while you're waiting for your lab. Yeah, let's do that. So do your lab and then come on to Schoology, watch the video on how to do your chemistry of the week and to go over the answers of your redox titration worksheet. Okay. All right, guys, have fun tomorrow in your lab. I'll see you later.